was a great and kind introduction. I'm glad to be visiting you, if only virtually, today. My research usually focuses on neutron stars, so this is one of the most extreme objects in the universe, and what the collision of those two stars can tell us about dense matter, about properties of neutrinos, and also the magnetic fields involved in it. And because I do a high-performance simulation, as Shinyu was alluding to, I typically like to start just by showing you one and just giving you some idea of what is actually going on in the collision. And so the scenario that we're in at is really the end of the life of two neutron stars as they orbit each other. What we can't see, what's going on at the moment, is that a lot of gravitational radiation is being emitted, carrying out energy and angular momentum. That means that the stars are moving ever closer together until they finally touch and merge. And at that point, when the stars collide, it's really like smashing two things together. There's all of this neutron-rich debris being smashed out, flying out, and ultimately undergoing our process nucleosynthesis. At the same time, at the center, you form this really hot and dense blob of nuclear matter that's rotating around. It's emitting ever more gravitational radiation. And what ultimately will happen is, because you're removing the angular momentum support, the star will collapse and form a black hole. What we could do now is, as the matter is setting down to this accretion disk, if we were to add in more magnetic fields, if we were to add in neutrinos, we could actually continue to track the system and then see how ultimately a jet would be launched and how that would give rise to a short gamma ray burst. But kind of to put everything into context, let me show you like the small cartoon, just focusing on each of the faces we've just seen in the movie and putting that a bit into context of what the observational channels are that can actually tell us something about the dynamics of the system. And so initially, as the stars are inspiraling, you're emitting gravitational radiation at a frequency of less than around 1 kilohertz. That's this inspiral signal. This is very exciting because it's actually something we have observed in this vanilla case that we saw in the movie for like 170817, first time in 2017. There was also a second one in 2019. But this is really cool because there are finite size imprints of the neutron star in that part of the gravitational wave signal. And this was used to study the properties of dense matter, put constraints on how big neutron stars are and how massive they can be. And so that's really inspired a whole line of research for many people there. The other thing that you can do is, and this is something that gravitational wave detections, either LIGO, advanced LIGO at design sensitivity, or future generation detectors will be able to pick up. This is the post-merger phase of the gravitational waveform. This is after the two stars have collided. You're going down from the orbital separation basically to the diameter of the star, so the frequency increases, and that probes the hot and dense phase of matter formed during this collision. And this is very akin to what is probed in collider experiments, really, so that can probe the fundamental states of matter, the QCD, the strong interaction, the phase diagram, and can tell us, for example, how quarks deconfine. Other things that we can do with this, and I will say a little bit more during the end of the talk, is we can also use that to systematically probe what matter is doing. I'll give some examples of that. The other thing is that after, in the case when the star is rotationally supported against the pull of gravity, and so if you remove that by means of angular momentum emission gravitational waves, you form this black hole disk system ultimately, then the story isn't over. The gravitational wave signal shuts off, but really now the dynamics just start to begin, because magnetic field instabilities will drive angular momentum transport in the disk, liberating like 30 to 50% of the disk mass that will ultimately become unbound. It's very neutron rich. It will undergo our process nucleosynthesis, and the heating will power a transient that has been observed in conjunction with that gravitational wave event. And that's a source of heavy elements. One of them particularly is gold. So it's really kind of an exciting thing because it gives you another window in how much mass was ejected, and that tells you something about the dynamics of the system, about the spins and so on. The other thing that has been observed was a short gamma ray burst. This is if later on you put enough magnetic flux on the black hole, maybe you get magnetically arrested, you launch a jet, and this generally can give rise to a short gamma ray burst emission. And we now know, I think there have been observations 3 years after the event confirming that this was a structured jet seen off axis. So this is really kind of a solid picture. The other thing, this is something that I very much like to think about, is something that another transient that has not been observed, but that could happen due to the interaction of magnetic fields during the inspiral of the stars. And effectively, it's all the magnetic hair that can get tangled up, and that can ultimately lead to precursor emission in terms of flares being launched from the merger site. And there's been a lot of work on that, also ongoing work. Now, the other thing is this was kind of the canonical system to think about, but there's actually not the full picture. The full picture really depends on what the initial masses and spins of the system are. And so the way to think about that is, if you vary the initial masses of the system, you can either make the stars so light that after they collapse, after they merge, they will form a star that will never collapse. It will be long-lived, will kind of stay there forever. This is one of the proposed sources for magnetars, because magnetic fields are being amplified during the merger. And so you end up with a rapidly rotating neutron star with very, very strong magnetic fields up to 10 to the 16, 17 Gauss. On the other hand, if you increase the initial masses, and that's kind of an interesting thing to think about, you start probing ever higher densities in terms of matter, but at the same time, you might become unstable, so that at the time where you collide the two stars, they can never really stabilize themselves against the pull of gravity and will immediately collapse and form a black hole disk system. And that scenario is very interesting because this is close to something that we have observed, and it allows us to set constraints on how massive neutron stars can be, and also constraints on the amount of disk mass that can be left around. So the major thing that changes in the picture that we had initially is, if you merge so massive stars that they immediately collapse, it's not clear if you retain a remnant disk. That will strongly depend on what the mass ratio are, what the spins in the system are, and you might get a suppressed afterglow, and you might not be able to feed a short gamma reverse. And so really the absence of those counterparts can actually tell you something about that system. And so the main thing that we need to understand there is sort of what's the amount of disk mass that is being left. And the way to distinguish that scenario from the other scenario is to kind of understand how massive neutron stars can be. So in general, the thing that we're talking about is really the maximum mass limit. What do I mean by that? We don't really know exactly what neutron star matter is made of, but if you take several different models, you can kind of solve the stellar structure equations, and you get a relation of how big a star is depending on its mass, which is shown here for different models of nuclear physics. And so the thing that we focus on here is now just to say, well, what's the upper line where this terminates? At which point does the star become unstable to gravitational collapse? And this really tells you something about this sort of prompt collapse threshold during the merger. If you wonder what kind of the number is that you have to expect, that you can actually get some inspiration or some actually hard facts from observations of massive pulsars. Typically, they're obtained by measurement of Shapiro delay. So you know that, for example, there have been observations of neutron stars with about 2 solar masses or a little bit larger than that. So really that tells you that there is like a lower limit on how massive neutron stars have to be. What you can then do, on the other hand, is you can say, well, in this first event, the 708-17, we have observed this structure jet, and so likely this requires a black hole in terms of collimation. And that means for those masses, it's 2.7 solar mass system initially, you need to have collapsed. You can make some simple back of the envelope estimates, and it shows you that the neutron stars initially cannot be more massive than 2.3 solar masses, because otherwise you would have never formed a black hole in the first place. You can kind of extend this and now relate the maximum mass of neutron stars to the scenario where we have 2 massive neutron stars crashing into each other, immediately collapsing, and you can kind of define what this threshold is. And there have been many proposals effectively relating this either to the compactness of the star or to the maximum mass. And so really this is sort of probing how compact can stars, so how small can stars be at most, and how massive can stars be. And so what we did recently is just a paper that got accepted in APJ letters, was to do one of the largest campaigns of numerical relativity simulations with 3 different equations of state, different mass ratios, and different initial spins, because that changes the angular momentum balance. It stabilizes the system against gravitational collapse, investigated what the precise relationship is. So at which point, depending on initial masses and spins, will immediately collapse. And it tells you something if you observe such a massive merger, what you would expect in terms of counterparts. Will there be enough mass around? And why this is really a relevant thing to think about, because you might say, well, looking at the distribution of galactic pulsars, maybe they're not as massive, at least on average. But we did have one event, the 1904-25, with a total mass of 3.4 solar masses that likely fell into that category, where either you collapse directly upon impact or shortly thereafter. And so kind of understanding those systems is quite important. Another question you can ask, and this goes a lot into the direction of what the lower mass gap looks like. So there's a proposed gap between the most massive neutron star and the lightest black hole. And you can ask, well, since the neutron star there is so massive, in principle, the gravitational wave observation is consistent with a 2.5 solar mass neutron star in that 1904-25 system, could that actually have been a black hole? Because if neutron stars cannot be more massive than 2.3 solar masses, that would be the only explanation if you don't want to invoke anything more exotic. And so the general question then is, if you just want to ask on a more abstract basis, can you actually distinguish a neutron star from a black hole in such a merger? And the simple answer is, if you had perfect knowledge of the gravitational waveform, you could, because the neutron stars have a finite size in terms of finite tidal deformability. So if you squeeze the neutron star under gravity, there's an additional term that pops up in your gravitational wave phase. It's proportional to this way of how much you can squeeze. It's called the tidal love number. And black holes have zero. So they're basically not deformable under tidal effects. And in principle, if you knew, or if you had a perfect detection, you could actually distinguish the two just based off of that and some constraints on nuclear physics. In practice, however, that's not the case because the signal is basically too noisy. Also for such high mass events, the tidal love number in total, like the tidal deformability, is suppressed with the total mass of the system. So instead, what you can think about, you can say, well, there's this optical counterpart. So if the gravitational waves cannot tell it apart, would there be a difference in sort of the electromagnetic fireworks I would expect after the merger? And that's something that I tried to answer just by performing the first numerical relativity simulation in that regime. So what you actually are interested in doing is you want to take a canonical system, say with a 1.4 solar mass neutron star and a very, very heavy neutron star, which is very challenging to simulate because you need to make sure that your numerics is accurate enough that it just doesn't collapse before you actually get to merger. And what you can then do is you can do the same simulation where you replace the neutron star with a black hole. And then you can really directly compare in terms of your matter dynamics, in terms of the gravitational waves, in terms of the mass that's being ejected, if the system for neutron star black hole is different from the system for neutron star. And the interesting thing there is you can actually make some analytical constraint because you can compute based on neutron star stability on the maximum mass corrected for effective spin, kind of where the transition is. I'd say which masses and which spins you can no longer have a neutron star given our current understanding of nuclear physics. And so the way that I approached this problem was to basically compute where this natural overlap region is. So given our understanding of nuclear physics, kind of how massive can a star be? And then you can kind of say, well, if I endow it with a little bit more spin, can be slightly more massive, but not too much. And then you can basically compute, say, the green region where you can have neutron stars and the black region where you cannot have neutron stars as a massive primary. And then what you do is you set up two systems, each of them containing a light neutron star and either heavy neutron star or heavy black hole with exactly the same parameters and spins. And it's really one of the most challenging numerical relativity simulations in terms of most massive neutron stars, the fastest spinning neutron stars. And we compared then what the difference in the system is across the entire parameter range. And the way you do this, in case you kind of are not familiar with all of the physics that goes in, just want to give you a quick heads up. So what you have to solve then in order to do this simulation, you have to solve Einstein's equations because you need to account for the gravitational waves that's being emitted, for the merger dynamics, you need to account for the fact that you might dynamically form a black hole. But then on top of that, because neutron stars are not black holes, we also have to model the hydrodynamics. So we have to solve conservation equation for energy and momentum for fluid. But then we also need to tell the computer that we're actually dealing with neutron matter and not, say, with a river that is flowing. And for that, you need to plug in a description of nuclear physics in terms of the equation of state. Typically depends on densities, temperatures, and nuclear composition. And you supplement that usually also by putting in electrodynamics, because especially when you think about long-term physics of the system, the long-term evolution, the magnetic fields will transport a lot of the angular momentum, and so will crucially determine the stability of the star, will crucially determine the amount of mass ejection you would get. So ideally, you also want to put that in. And because neutron matter is not just regular matter, but it's actually in weak equilibrium, this is your neutrons can beta decay, and because the densities are very high, they can also decay back. In terms of inverse beta decay, you need to include weak interactions as well. So really, you put in basically all the forces of nature on a computer, you simulate the system, and then using a code that I developed, and then you can actually draw conclusions from that. And so now getting back to our original question, really telling apart a neutron star merger from a neutron star black hole merger in the lower mass gap by again performing a numerical simulation, making all the gravitational parameters the same. So the black hole and the primary black hole and the primary neutron star have the same mass, they have the same spin, and so we can really make the direct comparison. And so just without further ado, I just show you what that looks like. Even if you've never seen such a simulation, let me just walk you through it. In the top row, you see this is a black hole neutron star merger. What happens is that as the neutron star approaches the black hole, it's being tidally disrupted. In this case, this happens outside of the innermost stable circular orbit. So actually some of the matter remains bound and will form an accretion disk. And part of this tail of matter that you see there is unbound. You're basically sloshing out this amount of matter, and that's something that then makes an optical counterpart, and this is something that you could potentially observe. And now we can do the very same thing, but replacing the black hole with a very massive neutron star having exactly the same mass and spin as the black hole. And then what you see is that instead of having just this one arm, which almost looks the same, you get a secondary arm of mass ejection going exactly the opposite way. And that's something that only happens if the primary is a neutron star and not a black hole. So you can just see by eye that there's a difference, and the difference is really the secondary sort of mass ejection that you get. It will turn out that this actually has very different properties than the main tidally driven mass ejection, the other arm. Now, this kind of feature is characteristic for all of the mergers. So if you do that for, say, different spins or different equations of state, it always happens. And one thing that we can see here, especially if we look at the lower panel, just see if this works. Especially if we look, say, at this part over here, just if you compare the distance that kind of this secondary arm has traveled to that difference of the distance of the main arm, you kind of see that those secondary ejecta must be moving much, much faster than the primary ejecta. And that's what makes them very, very interesting in terms of the nuclear physics that's being prompted. And so one of the things, however, to think about first before we address that point is, since most of the afterglow that's observable is driven by a liberating part of the disk that's being formed, you might ask, well, if you form different disks in the system, because you know there's a secondary component, maybe it's already different. But it actually turns out that given that you form the same black hole, you also get the same disk mass for that. And so that means that the entire subsequent evolution of those systems will be identical. Really, this means that there's the standard kind of kilonova afterglow will not be able to distinguish a neutron star from a black hole nature. However, going back to the fact that the secondary arm of mass ejection was moving much, much faster, as you can, for example, see here, that's a velocity histogram where you compare, say, for the solid lines is the neutron star, the dashed lines is the black hole neutron star. You can see that that matter is moving much, much faster at 0.6 times the speed of light or even more. And so those ejecta produce a distinct, different counterpart from the regular mass ejecta. However, of course, given that the secondary arm is sort of weaker, it comes from liberating the outer stars of the massive star. They also have lower masses overall. But what makes them so special is really that they give rise to two different distinct counterparts. One of them is that as this matter, which is moving really, really rapidly, shocks the interstellar medium, it can give rise to synchrotron and a radio afterglow. And this is something that happens about 3 years after the merger. And you know, you might guess for 1708-17, we already passed 3 years. And in fact, earlier this year, people have observed an X-ray rebrightening. In principle, you also need to wait if it's radio rebrightening to be sure if it's really just those fast ejecta or if it's just matter falling back, accreting at the Eddington luminosity. But in principle, it means that there's another counterpart in this picture that we haven't even accounted for. This really is exciting because that would, in that scenario, tell apart a neutron star from a black hole. The other thing, which is more challenging to observe, but in principle also possible, is as those fast ejecta propagate ahead of the kilonova, they don't partake in the up process. Instead, they directly beta decay, they produce additional heating, and that would give a neutron-powered kilonova precursor happening around a few hours after the merger. And so really this was different from the counterparts that you have in that case. The most challenging piece about that particular system we were studying there is that the ejecta are kind of too few to drive something that we expect to be observable. We are still thinking about exploring the parameter space because in principle, if you say you had a processing system or if you had a system with different overall masses, it could be that in fact you liberate more matter, but that's kind of the caveats I have to point out.
Elias?
Yes.
I want to ask a quick question on the last point that you had.
Yeah, sure.
So I think this is a basic question. So in the predictions which you show in the bottom right-hand plot, you're plotting the X-ray flux, and it looks like the prediction is that you have a rebrightening in the X-ray flux.
Yes.
Before you talked about all the processes which you talked about before are either like neutrino emission or radio emission. So what's the rebrightening in X-ray flux due to in terms of physics?
So the rebrightening here is very different from the standard afterglow. That's in that scenario, this is caused by the fast ejecta shocking the interstellar medium. So that happens much further out and it happens 3 years later. However, that rebrightening has to, in this scenario, be accompanied by an equal rebrightening also in radio that you would expect. And the difference is now that people have observed the X-ray rebrightening earlier this year. I think the first announcement was last December, but they have not seen the rebrightening in radio. And that sort of leaves the question open. Is it really that fast ejecta that's producing it? Or if you just compute the X-ray luminosity and you compare it to the Eddington luminosity of the accreting black hole, it's sort of the same. Or is it kind of fallback matter? that's accreting on the black hole. That's kind of an open thing. But from what I understand is there will be follow-up radio observations later this year. And so maybe we will know if it's rebrightening in radio also or not. Another thing we can kind of canonically ask is in this system, well, if it can potentially power a counterpart, if you have a disk that's left around, can it also give rise to a short gamma reburst? And there the question is, more generally, we have seen for a neutron star merger that there's a short gamma reburst, but for black hole neutron star mergers, it's not so clear, especially because the field strength in that system are generically lower. And so one of the things I try to understand is by performing one of the first simulations of neutron star black hole, putting the right equation of state and putting the neutrino physics in also, to see how does that system behave if after, let's say this is after 68 milliseconds when a disk begins to assemble, if you run that for longer, really do you get sort of an amplification of colloidal field? Do you actually form a magnetized region on top of the black hole that you would need? And so the way we tried to answer this was to perform a set of simulations, actually taking the ones that we already had for this mass gap scenario, just running them for much longer. This is showing the disk that you form after 100 milliseconds, where you really show that you amplify the toroidal and colloidal component of the magnetic field. And then you can, for example, one of the interesting things we found there was that the magnetic field in those disks obey statistical scaling relations with the density in the disk. And that's really cool because if you really want to do follow-up simulations of what matter looks like, or you want to understand what's the dependency of toroidal to colloidal field, you can actually just put in a simple prescription and really understand now, for example, that the toroidal field is significantly stronger than the colloidal. But the really cool thing is, if you run this thing for very long, let's say to 350 milliseconds, which is one of the longest simulations of that kind, you do see that the funnel region on top of the black hole. So if you look at the left panel, it shows you the amount of magnetization, so the ratio of basically magnetic pressure to fluid pressure, and that is increasing. And so you really see that the preconditions to eventually launch a jet are met in a way that the funnel is becoming force-free and it's clearing up. It's just that it also shows you it would take much, much longer than 350 milliseconds to actually reach a state where you could potentially launch a jet. So the question is somehow still open, but it sort of looks very, very promising because you can extrapolate it. And we found maybe after 500, 600 milliseconds, you would reach a state where, let's say, a region of about 200 kilometers in height would be magnetically dominated, which then would meet those conditions. So that's pretty cool.
Hi, Elias.
Yeah,
in this case, you show the polarized magnetic field can be amplified, but it seems like it's still this polarized magnetic field is not that coherent on the large scales, which is required for this kind of.
So what you're basically, okay, it's a bit hard to see what basically happens in the system. You don't get a clean, purely polarized field, but you get a twister shape. So the field geometry is helical. And you actually see there's a, if you look at that paper, I don't have it here now, there's actually a plot where you can see that the colloidal field strength in the funnel is increasing over time. So you do generate colloidal field, but the question that is still open for the disk is kind of how much colloidal field do you generate and how does a dynamo mechanism producing that colloidal field actually works? That's still an open thing. There was one study by Matthew Liska and also one by Christie in Northwestern, where they looked at a system with a lot of resolution starting from an initial toroidal field, and they showed that if you perfectly resolve the scales, there seems to be some sort of ballooning instability going on that produces effectively a large-scale colloidal field. But this is still not perfectly understood. It's also different initial field profiles than what we have here. That answers your question.
Yes.
Okay, perfect. And so with that, actually, let me go over to the second half of the talk. And that concerns itself not with the, so the first talk, what can we learn from the in-spiral? What can we learn from sort of present scenarios that we can detect? How do magnetic fields play a role? And how can we distinguish objects in the lower mass gap? And now I want to kind of go to the future and say, well, what actually happens if after the merger, we would observe this post-merger signal, which currently is at far too high frequencies to be inside of the sensitivity band of LIGO. And so the idea is, if you could probe this region, it would really tell you something about the most fundamental states of matter, because the matter probe in and after the collision reaches temperatures that are very, very hot, that are very dense, much denser than what you have in spiral neutron stars. So say if you were to do X-ray observations of isolated pulsars like NICER is doing, that would really be complementary because you're probing hot matter, so it's more like a collider experiment. And so that can give you constraints on what the nuclear matter is doing after the collision, and also of the properties of neutron stars. And the way you do this is you actually look at these post-merger peaks in the frequency spectrum, and those are correlated with effectively the properties of the nuclear matter. The way you have to think about this very simplistically is if you do observations of the solar chromosphere and you look at line spectra from line transitions of different elements, you basically look at that in the lab, you would do your experiment, you would kind of see what the lines are, and then maybe you correct depending on if it's the sun or if it's if it's more an object further away, you correct for Doppler shifts, but effectively compare just the line spectra, so the frequency peaks here, and you would say, well, that's that element. And for equations of state, you can do a very similar thing. You can simulate what the frequency spectrum is that would kind of correspond to your terrestrial experiment in the lab, and then you would compare that potentially in the future to a detection of the post-merger and identify what the nuclear matter is doing. And one of the things that I've been thinking about earlier this year, together with another postdoc here at Princeton and IS, Karen Rathel, was if you could use that to systematically understand properties of nuclear matter around saturation. What I mean by that is, this is probably the most kind of technical slide I have in this presentation, is if you look at the binding energy per nucleon. So you're really wondering if you had, let's say, nuclear matter, and you look at kind of what's the difference between purely neutron matter and symmetric matter, because matter around us in atoms has roughly equal number of protons and neutrons, but in neutron stars it's mainly neutrons, and you pay an energy penalty for basically stabilizing that matter given in terms of this nuclear symmetry. And so what physicists like to do is they like to Taylor expand everything, and this is typically what people think about, and then the relevant parameters are this S parameter of the nuclear symmetry energy and also the L parameter in terms of the slope of the nuclear symmetry energy. How is that really, what does that tell you? How is that expansion relevant? There was an experiment earlier this year that reported measurements of the neutron skin thickness of lead. It's called the PREX experiment. And so what they can do is they can basically relate this L parameter via some model assumptions to their experimental results. And they tell you that this L value is somewhere between 100 plus minus 40. And why is that relevant is because the size of the neutron star is really determined by kind of the outer layers of the star, and those are at those densities, and so are a sensitive probe for that parameter. So kind of closing the loop is basically what we're saying is, because if you look at the size of a neutron star and you compare that to the tidal deformability that you get from the gravitational wave signal, there's a degeneracy, there's a spread in that almost quasi-universal relation over here, and that spread goes with this slope of the symmetry energy parameter L. And so really, if you want to get a perfect interpretation of what you see in your in-spiral, ideally, you would also like to understand what that degeneracy is in terms of that parameter. And so our hope was, well, if the in-spiral is as this degeneracy, is that something we can get from the post-merger? So depending on what the precise conditions of your nuclear matter are, can we extract that from post-merger gravitational wave observations or from the amount of mass that's being ejected from the system in terms of the kilonova afterglow? And the way we went about this is to say, well, let's produce the first set of simulations and the descriptions of nuclear matter for simulations that can systematically vary parameters of the equation of state. Because one thing you have to know if you're not from this field is typically how it works is that nuclear physicists have very elaborate models in order to describe what nuclear matter higher than nuclear densities is doing. But that is typically motivated by different questions they're interested in. And so what you're really interested in from the astrophysical side is you would like to understand how big is your star, how massive is your star, and you would like to systematically vary the underlying nuclear physics parameters and then see how they are imprinted in observables and in the simulation. It's the first attempt that we did at this. And so the idea is you can draw almost by hand in the sense for the cold equation of state, different equations of state varying systematically in that nuclear parameter. And then the hope is that you see that in any of your observations. And so what this will actually do in terms of the neutron star sizes, so the equations of state were constructed in a specific way that we're looking at, for example, we're trying to make sure that in the in-spiral is comparable. So for example, for those 12-kilometer models, we made sure that all of these three equations of state that you can see over here had the same initial radius of about 12 kilometers. But then as you probe higher densities in the merger, the kind of size of the stars that you obtain after the collision is very, very different. It can differ by up to 1 kilometer in size. And then you can compare this, say, to initially having large stars or initially having small stars. And then really we get the entire kind of parameter range covered and get some first impression if you can, in principle, extract such parameters from future observations. So that's more really a proof of principle study. Right. One of the things I should also highlight here is that really crucially enabled that is that in that construction, we were actually able to account for finite temperature effects. If you want to have a simplistic kind of idea of why those are important is if you think in terms of your line spectra, just in terms of identifying different elements. If the source is moving away from you, you have to correct for a Doppler shift because your lines might get systematically shifted. Finite temperature in the equational state can do something very similar. If you don't account for this effect, basically your inference of those lines might be off systematically. And this is why you have to basically put a realistic thermal description of nuclear matter. And this is really, in that sense, the first unique construction we did, where you can both construct the cold part to model your properties of the inspiraling stars, and then add in all of the required nuclear physics to model the post-collision dynamics correctly. And that's really cool. And so then what we have done here is really to perform numerical relativity simulations of a 1708-17-like system, and actually characteristically look for those signatures in the post-merger evolution. If you kind of wonder, well, is there any difference that you would expect? The answer is yes, there is one. Even before you look into all of the detailed quantities, what this is showing you here is basically showing you the star formed after the merger. The green lines are contour lines of different densities and some funny nuclear physics units, but effectively it's showing you, if you just look at the geometry of those lines, geometry of the size of the star, you see that the star gets differently deformed. And this is very interesting because the initial merger geometry, having an unequal mass ratio, would tell you naively that the star should be very asymmetrically, and that determines kind of certain higher modes in the gravitational wave emission. For example, it determines that you get an m=1 mode. But then for one of the nuclear physics descriptions, this is completely wiped out in milliseconds after the merger, and you get perfect axisymmetry. And if you look at the bottom at the amount of temperatures that you probe, they're very, very different. And if you have 20 MeV difference in temperature, that can actually modify the cooling rate later on, and so it can also modify the neutrino emissions. And so really, the differences in the hot temperature physics and in this underlying nuclear parameters can affect how even the long-term evolution of the system is behaving. So that's really something important to think about. And then what we were wondering is, okay, the direct observables will be this afterglow and will be gravitational waves. So do these contain systematic imprints of the nuclear parameters? And one of the things that we found, which was very interesting, if you think again in terms of those fast ejecta in this neutron star versus neutron star black hole case, you find something very similar here in a way that differences in the outer layers of the star that are governed by this L parameter are directly affecting how much mass you're ejecting. And so if you wonder in terms of getting fast ejecta for the system, this will be crucially impacted by what your nuclear matter around saturation is doing. And so that basically means, and this is something that we're investigating right now in the follow-up work, is depending on how many or if or not you see those fast ejecta would actually give you a constraint directly on nuclear properties. So this is kind of using a new counterpart that was not used before to give you constraints on what the nuclear matter around saturation is able to do. It's kind of the first and only counterpart I'm aware of that can potentially do this. So that's really something very exciting. The other thing you can do, and this is really thinking ahead in the future, you can ask, well, if we can get this post-merger gravitational wave signal, could we actually distinguish different behaviors of nuclear matter? And so in the set of simulations that we did, you can just plot all of the different gravitational waveforms as a gravitational wave strain for the 2-2 mode. You can plot all of that on like next to each other. And even if you've never seen a gravitational waveform, you probably say, well, they sort of look different. They have different overtones, the different frequencies involved in the merger, and sort of the green ones look different than the blue ones, look different than the pink ones. However, you want to be a little bit more systematic in doing that comparison. And the way you can do this is you can use quasi-universality. What this is telling you is that the frequency spectra, just like your lines, in this case, satisfy quasi-universal relations. And so those quasi-universal relations tell you if you observe a certain peak spectrum at a frequency that roughly is supposed to tell you how big the star is. However, this relation comes with an uncertainty. It's not an exact curve, it has a certain spread. And the interesting thing that we found is when we did the systematic construction, where we considered equations of state never considered before in their form in any numerical simulation, you actually find that this pink curve differs very much from the red and from the green and the blue curve, although in the in-spiral, they almost look the same. And what it turns out is that basically those differences at high densities, for example, having this equation of state that is not straight, but it is backbent, behaves very, very differently. And what it would basically tell you is if we today had an observation of such a post-merger gravitational waveform, of a new gravitational wave event, and we would try to infer anything about dense matter, for example, for this equation of state, our current best fit that you find in the literature is off by almost 600, 700 meters. telling you basically that there's a systematic bias in all of the simulations that are currently being done. And so really what you should be aware of in that sense is if we're kind of not ready yet to even interpret what we're potentially will be observing in the future. And so what we need is we need to do a large campaign with sort of a more diverse set of equations of state to kind of nail down what the uncertainties are. Going a bit along those lines, I want to kind of highlight another effect that could happen if we had such a post-merger. And this is something that's not associated with the equation of state itself, but with dynamical corrections to the equation of state arising from neutrino processes. And so the way to think about this is that your neutron matter initially is effectively in weak equilibrium. So if you have an old star, then there are kind of neutrino beta decays and inverse beta decays are going on basically for millions of years. And so your star is in perfect weak equilibrium. However, after the merger, what happens is you basically heat up the matter, you're pushing the matter to higher densities, and locally you violate that equilibrium condition. So you effectively end up having too many neutrons at high densities. And what will happen is that your neutrino reactions, in particular a modified Orca process, which is an inverse beta decay, but it's energetically not possible. And so you need another, say, nucleon, say a proton or a neutron, to provide enough Fermi momentum for that decay to work, is trying to push you back to weak equilibrium. And what will happen if this process kicks in is it will cause an effective bulk viscosity that is changing potentially your merger dynamics. The way you have to think about this all sounds complicated. Effectively think about that as adding another term to your equation of state, so to your pressure that is acting on your nuclear matter. However, now that correction is given by the amount of local compression, so by the divergence of the velocity times a bulk viscosity that's given by the neutrinos. And so you get a dynamical correction that you cannot just incorporate by doing equation of state modeling that would dynamically arise during the merger. If you want to have a simple analogy of what or how this would affect you, just think about listening to me now. Think about how sound works. If you look at the dispersion relation for sound, because sound is a compressional wave, it will propagate at the sound speed, but then it has a damping part, it's this imaginary part, and that will go with a bulk viscosity. And so what a bulk viscosity to a compressional wave will do, it will dampen out the amplitude of this wave. So if you had a compressional oscillation, it would actually weaken and dampen out the oscillation itself. And so you can then define a characteristic timescale over which this happens. This goes with the sound speed, it's proportional to the frequency at which the oscillation is operating. But over this characteristic timescale tau, you'd basically damp out oscillations. And so the main question is then, well, those post-merger frequencies that we just saw that we want to use to understand dense matter are driven by those oscillations. And so obviously, if these neutrinos act like a bulk viscosity, it could very well be that they damp the post-merger oscillations, shifting the frequencies and corresponding basically to another sort of Doppler shift to your frequency spectrum that you have there. And that's something, if it's unaccounted for, would basically systematically bias any kind of inference of equation of state properties from post-merger gravitational waves. And the way you have to think about this, why this is so tricky, is because those neutrino processes depend very, very critically on the temperatures and densities this is being probed. These are bulk viscosity rates computed by one of my collaborators, Stephen Harris at INT Washington and Mark Alford at Wustel in St. Louis. And effectively what they managed to show is that depending on your description of nuclear matter and the finite temperature part, those effects can happen on timescales of 10 milliseconds, which are exactly the timescale over which you get the post-merger emission. However, it cannot be too hot because you can see, for example, here on the right, that this bulk viscosity is peaking around several times, about 1 to 2 times saturation and at specific temperatures. And so this is really something that will very strongly depend on the masses that you merge with and sort of the conditions that you probe during the merger and the equation of state that nature actually prefers. So the way then you have to think about this in terms of how is that actually going to damp your gravitational wave emission. So think about the two stars that are bouncing back and forth, so they're bouncing off each other. What those stars will do is it will basically cause a displacement of the initial star, it's this average R. And what happens is because the system is rotating and it's bar-shaped, it will emit gravitational waves, and the gravitational waves remove the angular momentum support, and they basically dampen out this bouncing off each other of the two stellar cores and ultimately allow the cores or the stars to fuse to one single star after the collision. And what you can do is you can say, well, actually, this thing happens to act just like a bulk viscosity because it's damping the oscillations of the two stars after the merger, after they have collided, and while they're fusing into one star. And you find that the characteristic timescale over which this is happening, so the characteristic timescale of your post-merger emission is about 30 milliseconds. It's something you can fit from any simulations that you have. And then what you can do is you can extract a number for this bulk viscosity, because so far we haven't really talked about how large the bulk viscosity is. And you get a number that has some very funny units, 10 to the 28 grams per centimeter second. The way you have to think about this number is this is your reference scale that your neutrino bulk viscosity would have to modify, because your system is effectively already viscous because of the gravitational wave emission. And so if your microphysics correct that, say if you had 10 to the 30 grams per centimeter second, which actually is what happens if you trigger the resonance of the neutrino modified Orca process, that would actually change your system. If you want a more fluid dynamicsy picture of that process, effectively what happens is that the gravitational waves produce an effective Reynolds number that's about 100 in the post-merger. Now the way to go about this is you can actually think about what is your bulk viscosity after the merger really doing, or is that really active? And so what we did is we took a state-of-the-art simulation of two colliding neutron stars, and we painted on after the fact without back reacting the bulk viscosity, because you just want to have an idea if the process is active or not. We painted on how much bulk viscosity would you expect. And the way we quantify this is to go to this bulk viscous ratio. And you can actually show that the bulk viscous ratio is related to the Reynolds number. So effectively this thing goes like velocity squared times inverse Reynolds number. And so we can directly measure what is the correction that neutrinos would do compared to the oscillation of the star that you already have. And so what you see at the top, this is really during the merger process. So the two stars are just crashing into each other. And you can basically see that in different regions over here, let me just highlight them again. In different regions, just during the collision, when you probe densities of about 1.5 times nuclear saturation, you get regions where this ratio is really, really high. So where you get bulk viscous ratio of 10 to the minus 2 and larger. And then during those oscillations, it's really active throughout the entire stars. It's really something that's not just kind of a fluke, it's really active throughout the entire stars as they are compressed. Now what you can then do is you can basically compare this to the local scale set by the gravitational wave emission, and you find that there's up to a 4 to 5% difference in pressure at the peak of the collision, really when you have maximum compression. Now that might not sound too large, but then again, on the other hand, we said that the Reynolds number, or the inverse Reynolds number, is about 10 to the minus 2. And so if you compare that, 10 to the minus 3 is actually not that small. And so really what we then found is that during the entire post-merger, so for several milliseconds, large amounts of bulk viscosity, independent of the nuclear physics model that we choose for that parameterization, were active. And so really the thing that we expect to happen is after the collision, the bulk viscosity could significantly affect your post-merger evolution. And then finally, just to conclude this talk, and let me also give you an outlook then, is how would we actually include this in our simulations? Because one of the things that is very challenging is to include effects of dissipation in the presence of relativity, because in principle, your standard fluid equations that you have in Newtonian hydrodynamics, like the Navier-Stokes equations, they're fundamentally governed by elliptical operators, meaning that they're not causal. In a way, if you were to look, for example, at putting dye in water and you look at the fundamental solution that's a Gaussian, then the Gaussian at large distances is immediately non-zero at any time after you put the dye in the first place. And that means that you get an acausal propagation. And so the interesting thing is that you can make this causal, and a lot of that progress comes from the nuclear physics community, because they have ultra-relativistic heavy ion collisions. And one thing that I did a few months ago, worked together with a very close friend from nuclear physics, Georgia Noronha from the University of Illinois, to design the first scheme in relativity that can simulate basically numerical relativity, numerical viscosity. This is all effects. This is bulk viscosity, shear viscosity, and heat conduction, and the anisotropies introduced by the magnetic fields. Something I don't have time to talk about today, but it's something that is quite interesting, because it really allows you to probe those regimes in numerical simulations in a perfectly causal way. And so with that, let me actually conclude. So what I was talking about today is telling you how you could potentially distinguish neutron star from black hole neutron star mergers in the lower mass gap. That's really cool because we've begun to observe events of that mass range where the primary neutron star could be very massive. And it turns out that there's one characteristic transient associated with fast ejecta that could distinguish the two systems. It's only that one, and it's something that we have potentially observed for the 170817 event. We don't know yet, but hopefully we know later this year. The other thing is that looking ahead in the future, if we want to learn something about dense matter, gravitational waves are actually a pretty good idea to tell us something about that. However, if you do a really systematic study, and we did the first of its kind in that sense by varying systematically the nuclear parameters, you actually find that there are large degeneracies, and our understanding could still be potentially biased by basically having violations of quasi-universal relations at the moment. And so it tells us we need to do more work, more systematic parameter scans, and effectively we need to explore the entire parameter space to get ready for those observations. And then finally, there might be corrections, I'm not even mentioning here, but that might be really exciting due to neutrino effects, effectively modified Urca, pushing you back into weak equilibrium, something you cannot put in your equation of state, but it only arises dynamically due to the dynamics of the merger. And so what that would eventually tell you, if you don't account for it, is that you would get a systematic shift in your gravitational wave frequencies. And that's something that we're also trying to simulate and get some idea of how large that correction would actually be in the post-merger phase. So with that, thanks a lot all for coming and for inviting me.
Yeah, thanks, Elias, for this wonderful talk. Let's give them a clap. Now let's open the floor to the audience and let's see if anybody has any questions. Hey, Amok.
Hi, Elias. So first of all, awesome talk, very interesting. I want to take you back to one of the suggestions that you made that magnetars could be the result of neutron star mergers. Now, my problem with this idea is that the rate of neutron star mergers is very small. The lifetime of magnetars is also short, and yet, even just in our galaxy, we see about 30 magnetars. So how does this model explain the observed population of magnetars, the galactic magnetars?
It doesn't have to explain all of them, but what I was basically making as a comment is that if you had a system that was not rotationally supported because you merge two 1 solar mass neutron stars, say a 1.1 solar mass neutron stars, their spin down will actually not remove your rotational support, and so you run in no danger of ever collapsing. So you would actually get a neutron star that is stable, has a very strong magnetic field, and the strong magnetic field would come from the merger. It doesn't have to explain all of them, but it's literally what would happen if you had such a system that would merge. Just to clarify.
Oh, so you're saying that there's another channel to produce magnetars? I see.
Okay, for sure, but that system is capable of at least contributing to that. Yeah.
Okay, JJ, I saw you raise your hand.
Yeah, wonderful talk. So I guess I had just a technical question. When you were talking about in your simulations, when the stars start to merge, they do this kind of bouncing phenomenon. Do you have to do anything specific in your simulations when the two neutron stars start to merge with respect to one another, or do your simulations just naturally take into account any sort of like interface conditions or anything like that?
So the nice thing is we're really solving fully compressional hydrodynamics that can in a dynamical relativity background. So that means we can both account for the space-time merging and for the stars merging, producing, let's say, the hot temperatures at the interface. It all comes out very naturally from the simulation. What we don't take into account is that we model the entire star as a fluid. So for example, if you think about you had a solid crust that would crack before the merger due to tidal forces, that's something we're not accounting for. So in that sense, we don't have to do anything special, but our model is very simplistic in terms of what happens at the actual point of collision.
Go ahead, JT.
Yeah, I was just going to ask a question to that. Do you have any speculation about what happens if you include the effects of the crust when these two neutron stars are merging?
Yeah, one of the really cool things that could happen is if you have a crustal cracking right before you actually have the merger, they would likely shake your magnetic field lines. And there have been like ideas of basically launching alpha waves that become nonlinear in the outer magnetosphere. And so likely what that would do is it would cause a precursor transient. because the crustal cracking happens before you have the actual merger, like tidal forces should be enough for that. There was like a paper a few years ago, I think led by Tanja Hinderer and others, giving some estimates on the energy of that.
Okay, so then Aaron and then Dick.
Hi, thanks for a great talk. First, I have a question and then a comment. My question is, I'm very interested in these fast-moving ejecta that effectively freeze out the R process. But I was wondering if you could maybe say a little bit more if you've looked into it on what fraction of the neutron star merger parameter space we expect to actually have, of order 10 to the minus 3, 10 to the minus 4 solar masses of this material that would be detectable. Because you made a comment that they don't really reach. Not enough material is really accelerated to these velocities, but can we expect that to happen ever?
So in the neutron star black hole case, in that particular case, neutron star kind of neutron star black hole mimicker in the lower mass gap, this was more challenged because you basically had a very tightly bound, gravitational bound star. If you look at an equal mass case, like in this case, for example, you get very naturally a lot of strong mass ejection also for fast ejecta. And one of the things that we're trying to understand right now, because it's not exactly clear what is actually driving the fast mass ejection, is to systematically vary different parts of the physics parameters. So it's sort of an open problem. There was one attempt in conjunction with this X-ray rebrightening done by the group of David Radice and Sebastiano Bernuzzi to look at their database and find if there was any systematics. But there, the problem is that the equations of state vary so heavily that yes, you do get fast ejecta, but you didn't really understood like under which condition you would actually produce them. But so yes, it certainly is expected that those things are being produced in copious amounts for those events, but just not for the case where you have very unequal masses. It's more like the equal mass case that produces that.
Thank you. And I also wanted to comment that, to be clear, there is not yet really evidence for a rebrightening.
No, there is.
There's evidence for a flattening and an excess with respect to a decay, but at least with respect to the data that's been published, we can't. And you can even see on your figure, that
is true. Basically, there are these few data points, and they almost look like a rise. I like to be optimistic in that sense, but yes.
No. I'm not trying to be a downer. I just want to make it clear because we haven't yet actually observed the rebrightening. I hope we do, and we probably will, maybe.
Okay, Dick.
I wanted to ask you about the neutrino transport and the viscosity. So maybe to the viscosity first. Are you saying that the viscosity, there are always bulk viscosity corrections to pressure, and you're saying in this instant it can be large, which is really interesting. But then you only looked at the modified Urca process. What about the other processes of relevance to the neutrinos and that give a viscosity?
Okay, I don't have the figure now, but so basically the dominant channel would actually be direct Urca. The problem of direct Urca is that it only is active at higher density.
Yeah, I realize that, but what about, is it because of the way the modified Urca is treating the electron-proton balance with the neutrons? Because there's also NN into NN nu bar, which is nucleon bremsstrahling. Is that not relevant here?
I think that one is subdominant.
I actually don't. Well, it depends what YE is, of course.
It depends on the electron.
So maybe that I don't want to go too far in that direction. What is the YE in these really hot merging environments?
Yeah, so the YE that you end up with after the merger is 0.1 and lower.
So it's still neutron dominated.
It is still neutron dominated, but
so that's so that means that the NN into NN nu bar may not be so small, but it's something that, it's something to look into, or maybe you already have. So then the other question is, this is a really dynamical situation in which the neutrino transport is non-trivial. And how is it that you're treating it in the non-viscosity kind of framework when it is breaking out?
So in those simulations that I'm doing, I'm not accounting for free streaming neutrinos. Basically, what those simulations are doing is they're assuming that the neutrinos are locally in thermal equilibrium with the matter, and then you subtract a statistical correction, and that basically corrects for the electron fraction.
So nothing even like a flux limited diffusion?
It's not even a flux limited diffusion. But the important point about the modified workup process is that this is something that is currently not modeled in any of even the kind of more advanced schemes. So even if I would have the best neutrino transport on the market in those simulations, those effects would not pop up. And this is why we're thinking about putting them in effectively.
Well, actually, yeah, that may be true, but it may also be true that effectively you would end up with the viscous modification because of having a
direct workup for sure, yes.
Well, I'm not sure, maybe the other one too, because the process is there. The process would be there in the transport.
No, the modified Orca interaction is not in current codes.
It should be.
But it is not.
Okay.
I agree with you. Ultimately, if we would put all of the neutrino physics in, we wouldn't have to do this. But
yeah, just saying it another simple way, these things have long been used in neutron star cooling. And so you'd expect, what are we dealing with? Neutron star cooling. It's just that it's happening rapidly because it's a dynamical system. Anyway, okay, it's interesting. And what's encouraging is that, by the way, I really did like the talk. It was fantastic, covered so much material, but at least there are a few things still to do. Game's not over.
Which is good, so
yeah.
Enough to work on.
Okay, do you have any more questions from the audience? Okay, if not, let's thank Elias again. And there are also a few in-person meeting slots with Elias tomorrow if you would like to chat with him, so you can sign up. Yeah, thanks, Elias.